guys, this is our senior project. It's also a Raytheon project, and we are Team 2, What the Drone Doing.
Hi guys, I'm Ramon.
I'm Pi.
I'm Alarik.
I'm Prof.
And I'm Colin.
The whole point of the project is to make a self-autonomous driving drone that's supposed to blast water onto the ground vehicle. The drone is based on, we're building it based on components that we researched and acquired. Team is selected based on an interest and previous research and development experience, and it is to aid Raytheon in research purposes.
Hey, Lark here. I am responsible for the power distribution for the drone. We named it powertrain design, but practically I'm responsible for any power being distributed to any components. Biggest concern being the motors currently, because they do take up a lot of power. I also have to be responsible for other components like the Raspberry Pi 4 and the P-Hawk 4. I'm also the team leader for this project. We've developed a 7-inch drone, and we do plan to do an 11-inch drone. Originally we wanted to do a 5-inch drone, but that didn't give us enough space to add additional components, so we went with 11 inches. So the point of this project is to build an autonomous drone that seeks specified ground vehicles and delivers a payload of water, practically just drowning it in water. There's 4 challenges, and there's a bonus challenge. All challenges deal with 4 vehicles moving in a certain manner. Each challenge becomes more difficult in succession. The reason why it's more difficult because ground vehicles do move around a lot more with each successive challenge. So challenge number 1, ground vehicles are not moving at all, and the drone must detect these ground vehicles in a certain order and spray water onto them. Not that difficult a challenge. Challenge 2, this is when things get a little bit harder. No, it doesn't look harder, just the drone moves in a line. Not the drone, the ground vehicles move in a line, and the drone must detect these ground vehicles in sequential order once again and spray them in the sequential order specified by Raytheon. Challenge 3, it gets a little bit more difficult. These ground vehicles are told to go in a straight line, then a rough 90-degree angle, and then another rough 90-degree angle. So while that ground vehicle is doing that, the drone must detect the ground vehicles and still spray water onto them in a sequential order. And the last challenge is the hardest one of them all. Once again, the ground vehicles are going in a straight line, a rough 90-degree angle, but in this 90-degree angle change, it can be there for a little bit longer than expected. On the previous challenge that you see, it's just very rare. It's like 90-degree angles for like maybe a few seconds to go back to the original straight line you had in mind. In challenge 4, it's more like there's no specified time, so they could be in this 90-degree angle going down for like who knows how long, and then it'll be in the straight line. You can have 2 drones even touching each other at some point. And the drone that we build has to detect that and attack in the sequential order. Spray water. And the bonus we don't have here, but the bonus is practically these drones. These ground vehicles are just moving all over the place. There's no structure of how they should take their turns or whatnot. They can go anywhere, and the drones was detected.
Hello everyone, I'm Pi Oliver. I'm the project manager, systems and verification engineer, and I will oversee the systems level integration of the project. I'll help assist with the communication, scheduling, the logistics, requirements, some of the risk and safety procedures, and help with the overall success. I'm also responsible for developing the interfaces for all of our subsystems to work together using CAD software, and also helping make sure that all the hardware and software communicate effectively. And I'm also going to be contributing to the computer vision subsystem that the drone will use to see and perceive its 3D environment, as well as track the individual ground drones during our challenges and navigate around. Here is our first semester project schedule. We are already past August, September, October. We are actually ahead of schedule in that we are already prototyping right now, even though prototyping is scheduled to start by Raytheon in December. However, we already have many of our components and many subsystems developed, so we're working on integrating those so that we can test our drone as fast as possible and stay ahead of the curve with regard to our spring demo challenges, which are upcoming next semester. Here's our preliminary block diagram. We have 5 main subsystems: the flight controller, the power management, the central computer, instrument package, and water blast subsystems. The flight controller will be responsible for navigation, power management is for safety and making sure we have power to everything. The instrument package will contain the visual sensors. The water blast subsystem will help deliver water to ground vehicles in accordance with the challenges, and the central computer will help arbitrate all the decision making between those other subsystems. For the computer vision subsystem, we have plans to purchase and use the Oak D Lite stereo camera for the use as the primary visual sensor, and we want to acquire an NVIDIA Jetson Nano to use as the hardware acceleration module for the computer vision subsystem, because the Raspberry Pi is powerful but not quite optimized for visual data. So NVIDIA's GPU cores and tensor cores inside the Jetson Nano will help us accelerate that hardware processing and navigate much faster in real time, on the order of 60 frames per second, as opposed to something like 15 or 12 FPS, which is theoretically possible with the Raspberry Pi. For the system integration, all the interfaces between all the components and subsystems must be specified. We will need to develop novel interfaces for some of the components, including the electronic speed controllers, as well as other things that need to be mounted on the drone frame but aren't currently designed for the drone frame. So we imported our design into SolidWorks and are refining it, as well as modeling it for simulation purposes, and to develop these new parts to help us be able to get everything mounted and balanced on the drone as necessary.
Hi everyone, my name is Ramirez, and I'm part of the drone design team, and I'm also a solo member of the safety team. Me and Alarik are part of the drone design team, and we ensure like everything related with the drone, all the parts match up and they fit perfectly, and they will like work well together. We will also potentially pivot if we feel like they don't work together. I'm also a solo member of the safety team. We realized slowly that we needed. Hi class. So this is a schematic for our drone. It's based off the Pixhawk 6X. The reason why we use the Pixhawk 6X is because it fits our needs, and we felt like it was the best flight controller. What's connected to Pixhawk 6X is motors, propellers, the telemetry kit, batteries, and the ESC. What you also might see is that it's connected with the LiDAR. We are not using LiDAR. We're going to use a completely different computer vision, which will be talked about shortly. This is what we have purchased so far. As mentioned, we have purchased the flight controller, the motors, propellers, as well as the ESC and a chassis. We also purchased Raspberry Pi 5s, but they're also back ordered right now, so we don't know when they're going to come in. We were hoping to get our drone flying by the end of October, but the parts weren't able to come in, and also we had school issues. And then we realized while we were building this drone that this drone has carbon fiber on it. And carbon fiber, if it was moving at a fast enough speed, can cut like a knife. So we needed to actually add a safety proponent to our team. So some safety things we're going to try to focus on is we just need a safe location at Cal State Long Beach or at another location where it's free of people. We need to make sure the battery is disconnected until it's ready to fly. And then again, we for sure make sure there's no people around, because we don't want to hit anyone with our drone. And as well as us, we need to maintain a safe distance from our drone. Thank you.
Hi, my name is Colin Bender. I handle the programming for our autonomous UAV, more specifically the flight control and accomplishing the objectives as outlined by the competition rules. I will develop the logic for the drone to complete the competition tasks using open source software packages such as DroneKit and ArduPilot, and I will also perform simulations in software environments like Gazebo and ROS to safely test our drone without fear of damage. Since our last presentation, what's been accomplished so far on the software side of things, I have loaded the firmware onto our flight controller so that it can effectively communicate with the motors, power module, and all the other mechanical parts of our drone and control them without any worry. I've also installed DroneKit, which is an open source API for creating and planning drone missions on autonomous flight, very useful for developing the scripts that will be used to carry out the competition objectives. I've also installed Gazebo and ROS, two software packages. Gazebo is an open source 3D robotics simulator, and ROS, which stands for Robotic Operating System, is a framework for developing software for robots, such as the autonomous UAV in our project. The next major things I have to do on the software side is establish a communication link between our flight controller and our companion single board computer, such as a Raspberry Pi or an NVIDIA Jetson Nano. This can be done with software like APsync and MavProxy, both of which use the Mavlink protocol to communicate between these devices. Additionally, make sure that all the other modules necessary for this communication, such as telemetry radios and GPS modules, are properly installed within our drone. I have to continue testing the example scripts provided by DroneKit, especially while connected to the flight controller, to make sure that everything is working properly, everything is wired up, and the scripts can run without any issue. If they don't work, then I will examine potential alternatives for our autopilot software, things like PX4 and ArchiePilot. And in terms of our long-term challenges, one of the main ones is our computer vision subsystem. Refining the way the drone will be able to detect the ground vehicles. In the competition rules, we have to make sure it identifies our specific school ground vehicle and only targets that one, no other ones. So a lot of work to be done in terms of creating scripts that run on our drone and properly seek out the ground vehicle without targeting any of the other ground vehicles. Additionally, I have to do a lot of rigorous simulation and testing of our drone in simulation environments. Ideally, create a one-to-one model of our drone in simulation so that we can test all the physical effects of flying on it before we actually have to go out and fly it physically, so that we don't have to worry about any potential surprise factors that would damage the drone. And once all that's been done, then actually flying the drone physically in the air and running the scripts.
Hi guys, I'm Ramon once again, and I will be taking charge of the chassis design, which means all the components will be housed in the frame and how they are balanced and everything like that, as well as designing the water gun system or water blast design. Alright, so what has been accomplished since the last time that we've spoken? So all parts have been ordered for the drone prototype. Since our first objective is to just get a flying drone up in the sky, we decided to go with a pre-built chassis so that we can just get something up in the sky without having to incorporate any of the water blast designs or any of the sensors or cameras. And during this time, I have been deliberately researching different methods of creating that water blast, whether it is using a straight water release that will just go straight down using gravity to our advantage, or by incorporating a water gun design so that it can be shot at an angle with better precision. As well as things that I have done, I have installed SolidWorks to start making those CAD designs, which would include the water reservoir and turbine system. Alright, so as far as what is next on my agenda, I am going to start making those CAD designs using SolidWorks for that water reservoir that will house all 20 milliliters of water for all targets. So each target has to be hit with 20 milliliters of water for it to be detected as a hit. As well as designing a turbine / water gun motor, which is really just using DC motors and turning them on and off for a certain amount of time, which we will calculate to determine how much 20 milliliters is. Raytheon has made it clear that they're still revising on how the water detection system will be done, whether at first it was that the ground vehicles, once they get hit with 20 milliliters of water, it will send a signal indicating that they have been hit, but at the moment they have leaned towards the drone being the one to be able to detect if it has been hit or not. So still a little unclear. As well as for the final part of what's coming up is we're trying to also redesign the chassis for on the prototype that will house the sensors and cameras, making sure everything is balanced as well. And finally, as far as future plans, once we have a flying drone, we are going to start incorporating those flight paths that the drone will have to do in order to detect all of the ground vehicles, as well as determining how they will be affected by wind resistance and how all of the housed units will be balanced in regard to that. We want to also be able to build a second drone so that if anything happens to that first drone during the practicing of the challenges, we want to have a secondary drone so that if anything happens to that first drone, we have a backup. And lastly, we want to construct a final prototype for the chassis design that will house all the sensors, the cameras, as well as implement the water blast design. As far as you can see in the picture here, it is taken from another school to show you the different designs as far as how you incorporate all of the different sensors and cameras and the different markers that will be used in order to determine which ground vehicle we are trying to blast.
Thank you, everyone. Again, we are Team 2, What the Drone Doing, and we appreciate you taking the time to participate and view in our project progress report 2 for our Raytheon drone competition, and we hope to represent Long Beach State and lead the university's success in the drone competition next spring. Go Beach!
Go Beach! Go Beach!